All right, so I ask you to refer the PDF, and I gave you a few sessions, right? So how to remember the formulas. The basic idea is like when the data need to be considered and is going to come in sequential form, that it depends, like the existing one depends on the previous set of data. Then this RNN comes into picture. The regular neural network will not help us much. Whereas RNN by itself is going to consider the not just the its own input data, it's going to consider even the hidden layer, the past hidden layer. If it is if it's from the start, obviously the first one is going to be zero. The hidden layer state is going to be zero. So we discussed about this, and what we need to discuss is like I think we discussed even about vanishing gradient problem. There is a problem with RNN. The problem is that it's going to, we'll come back to backward propagation later. One, if it is a simple sentence, RNN works. In fact, it has very less number of parameters. Even if you look at this one, it has comparatively uh, a simple RNN, 7,000 parameters, whereas LSTM is 29,000, GRE is 20,000. So comparatively, it has very less number of parameters, but how accurate it is, that is what matters. If you look, if it is a simple sentence, RNN definitely works. If it is a long sentence, it's difficult to remember the previous one. So it's not going to help us in finding out. In this case, it has to defer to this word that it's going to find out that it's Japanese, right? So then another problem, the reason for that obviously is the vanishing gradient problem. In fact, there is, where is it? We use sigmoid heavily here. Where is it? Okay, maybe find out somewhere else. Okay, then why we need LSTM? Obviously, to remember even a long-term thing. So it has to remember even in this particular case, it's Japan. It has to remember Japan so that it can find out it's Japanese. It's going to predict Japanese. But how it's going to remember? Obviously, like on top of RNN, we got LSTM. The idea behind LSTM is to forget what is not necessary and remember only what is necessary. We have three gates here and memory state. Forget gate is going to help us in finding out what has to forget, we have to forget, and what has to, no, the input gate, and the output gate is going to be the final one. So that is the final, I mean to say, whatever that has to remember, so that will be the final product of it. And when it comes to this one, I prepared few, I kept all the formulas in this one. So basic idea is to, no, not this, yeah. How I got this LSTM here? I'm sorry for that. So it's actually forget gate. I think I have, instead of forget gate, I have added reset gate. All right. So forget gate is the same formula. We are going to apply sigmoid, which is an activation function. Whenever you see sigma, it is sigmoid activation function. Whenever you see tan H, it is tan H activation function. WF into weight of that particular no forget gate into HT minus 1, the previous hidden state, plus weight of WF into XT. That gives forget gate. Plus, of course, it will have its own bias. Same way, we have the input gate. Same thing like the sigmoid. Wi into HT minus 1 plus Wi into XT plus bias. And apart from forget and input gate, we need to find out the candidate hidden state. 10H into WC into HT minus 1. This is basically for memory kind of. So this CT tilde is basically here, comes here, this one. This will help us what need to be remember, and this will help us what has to be forget. The CT minus 1 comes from the previous state, previous cell state. The previous cell state, if it's not been there, if it is from the start, if it is the first one, then the CT minus 1 is going to be 0. So we not to forget anything. That is what it means. If it is for the first word in the sentence, right? So memory to be added and memory to be discarded, that will be the cell state. So no, it's not going to stop over there. So it's going to stop, like we need to continue even for output gate. Output gate is again sigmoid activation function. WO is the weight for that particular output gate in that particular neuron into HT-1 plus WO into XT plus BO. So this output gate and this cell state, so this is going to be the final one. So HT equal to OT into 10H into OT of CT. Basically, every cell state is going to yield out CT minus 1 and HT minus 1. In this case, it is HT and this is going to be CT. This CT is going to be forward into the next cell, next block, and HT is going to be forward to the next block. This is going to be the final hidden state, right? So there is one slight change when it comes to the same LSTM, but this is not widely been used. And if it comes to this one, you can see that earlier we used to consider only HT minus 1, right? In this case, the original LSTM. Whereas in peephole architecture in this is slight changes to the original one. So we have added even CT minus 1. So in this case, what will happen? So it's going to be sigmoid activation function WF into CT minus 1 plus WF into HT minus 1 plus WF into XT. Usually we calculate only WF into HT minus in the previous hidden state plus WF into XT. Whereas in this case, we are even including CT minus 1 also. That is people architecture. When it comes to GRU, there are only two gates in this case. One is reset gate, again sigmoid activation function, WR into HT minus 1 plus WR into XT. WR means for reset gate plus BR. The same way we have update gate, which is going to be represented with ZT. It's sigmoid activation function WZ into HT minus 1 plus WZ into XT plus BZ. Z is because it has been represented with Z. There would have been some reason why it's not been represented with U. The next one is the candidate hidden state. So we need to consider both a reset gate. Is that one? Yeah, finally we are going to consider. Okay, so he candidate hidden state. We are going to consider only the reset gate. WH in its own weight into RT. This one into plus. Sorry, it's basically like WH into RT plus WH into HT minus 1 plus WH into XT plus BH. The final hidden state is going to consider the candidate hidden state. So it's going to consider this particular update gate, right? 1 minus ZT into HT minus 1 plus ZT into HT. And the basic idea is to consider some part of the previous hidden state. Because it has only two gates, short reset gate and update gate. A reset gate is basically like, forget gate plus this one. And where is that? Yeah, forget gate. And there's another, where is it? Insert gate. So basically, reset gate is basically a combination of forget gate and input gate. Right? And sorry, reset gate is basically forget gate, input gate, yes. And no, for input gate and forget gate been combined to for your update gate, and reset gate came later. That is how it got two gates. One, this will remember short long-term dependencies, and this will remember short-term dependencies. Even though it reduces the drastic number of neurons, if you look at this 29,000 compared to GRU 22,000, LSTM most of the time works. So in our case, basically, it's better to implement and find out which one will better, which one will work. Again, we need to consider the number of parameters because the model size will increase. So when you deploy it in your production for inference or even for training, thing is that it demands a lot of resources. So based on the practical, limitations, you need to judge which one will work better. In this case, I have given script for all. And this is basically for time series. Time series in the sense, this consider this is the target variable, wherein it depends on the previous thing. I mean to say, the previous time. Suppose this data, you can see that this one has some influence on this one, whereas this one has influence on this one, right? So it basically depends on the previous time. So that's why it's been called as time series. The same logic applies for even for text data. A word being going, we need to it depends on the previous word or previous letter, right? So we have taken the data, and in this particular case, I think it's on closed one. So we need to find out the next value. So that is what we need to predict it. So what we did here is we have applied the regular pre-processing stuff. Apart from it, for RNN, we have used simple RNN. That is again been imported from TensorFlow, simple RNN. Again, the same thing, LSTM and GR is available here. There's no other difference apart from, adding simple RNN. Usually we go with directly like this, right? We directly supply this without being wrapped in simple RNN. And we need to wrap it in simple RNN. That's the only difference when it comes to implementation. Apart from it, if you can see the same thing, same stuff. So this is going to be like a number of we have number of columns, input columns. First hidden layer is going to have 32 neurons. Second hidden layer is going to have 32 neurons. 32 again another 32, and finally it's going to be the output layer. And we have used atom optimizer, mean squared error loss to find out the loss here. When it comes to LSTM, it's the same thing. There's no difference except the LSTM bit added. Implementation part is quite easy. And instead of LSTM, we have used GRU. But the number of parameters obviously changes, right? Because it does not require too many gates. That's the only difference. The model training for all the three. And finally, we try to compare it. In this case, GRU is more promising. Yeah, GRU is more promising. So you can pick, a GRU model compared to LSTM or RNN. Any questions? I will re-upload this one because I think by mistake I would have copied right here. I need to add the input gate, forget gate, and all here. You not just if you understand the logic, that is more than enough. So sigmoid is the activation function. Sigmoid again activation function. Here he applied tan h. The formula is same, except people architecture wherein they considered even CT minus one. That's all. Apart from it, if you remember the number of gates and few memory cells here and there, that is more than enough. Any questions?
So the activation function should only be sigmoid, or it can be any other?
This particular architecture, they pick the sigmoid, but if you take this one, internally they are going to use sigmoid itself. So it's not manual one, right? So it's not that you have to pick, we haven't mentioned any activation function here, isn't it? So it's internally going to be,
Mhm.
sigmoid or whatever they have used. So we are utilizing the architecture built by someone else, not directly by us. Earlier, it used to be that we're going to have complete control on our architecture. Now we are relying on someone else, so we need to use that one. If you want it, obviously you need to build it from scratch. The LSTM architecture implementation. It's very quite difficult, in fact, to build it. You can't tweak it, at least for now.
Okay.
Any other questions? Okay, even though this is a very short session, um, I think because of the previous explanation on RNN, that help us to understand this much faster. So only thing is, you need to remember these sequence: input gate, output gate, forget. When it comes to the remaining part, it's quite simple. This is going to be the input, and this is going to HT and CT is going to be even though it's output, it's going to feed as an input to the next one, right? And we know forget gate, input gate, and output gate. Apart from it, we need to understand the candidate cell state and hidden cell state. We need to calculate CT and hidden cell state that both combined together, affects HT. So go through the formulas. If you have any questions, let me know. And tomorrow we will start NLP.
So what is NLP is about? Like just
It's
briefly.
a natural language processing, text data. So completely going to be on text data. So our course is more on generative AI, right? Generative AI specialization. So it's
So that is
predominantly is
NLP
LLM.
based.
Yeah, text. Anything that is related to text comes
Yes.
under NLP. In fact, originally NLP. Later on, they started giving started calling it as LLM because the model become very large. So large language models. In fact, it comes under domain called NLP, natural language processing. Anything simple words in simple terms, text data using deep learning or machine learning to handle text data.
So what is Hugging Face? Yesterday when I was reading something, I got that.
Hugging Face, they provide open source models. Someone will train the model, they directly provide the model. So rather than building our own and building and the final product is going to be model, right? We can utilize someone else built model. Here, if you go to models, there are different categories, various categories here. Text classification, we have a lot of models. We can share our models right here. There are even good organizations like Facebook, even they share that. So rather than building our own, we can utilize these models.
Will we
Like,
learn about this in this course?
yeah, it's part of the course.
Okay.
Without Hugging Face, LLM is not going to be complete because there is number one hub. No, I can say it's online hub for LLMs, especially. Even though they have support for audio and all, it's not really working well. So it's most predominantly we need to look at this one, NLP, natural language processing. This category is very important. All
Okay.
right. Yeah. Any other questions?
No.
And here I have given time series example. Don't worry about it. This course is not time series. Just give an example. And when it comes to text data, you will see a lot of projects on that. So if you're worrying about using RNN or LSTM or GRU on text data, don't worry for now. All right. That's it from my end. If you have questions, let me know. Or else you can log off. This is a very short session, but it's better to start from tomorrow when it comes to NLP. Go through the PDF. Maybe like interview perspective, you have to learn. When it comes to implementation, it's quite easy. It's regular
So
neural
in
network.
respect
Yeah.
to what should we remember about this one, like formulas and all
Gates.
that?
Yeah, these formulas need to remember how many gates and how many, the flow, the whole flow.
The diagram itself.
If you don't remember the diagram, it's difficult to understand the flow. This will
Yeah.
diagram will help us to understand the flow, right?
Yes, sir. Okay. Okay. Thank you.
Sir,
Yeah, please.
sir, one question, sir. In RNN, so that previous state information is also going inside it, and at first we decide our means any random weights and all those are given, and so means how we can means train that means with our data set means practically means how it was happen.
In fact, so you're speaking about the previous state, right? So
Yes,
we haven't started LLMs. Tomorrow was LLM, tomorrow we'll start NLP. It's going to be for a week, and thereafter we will really get into LLMs. Then you will understand it, like how to implement it.
okay. Yeah.
Yeah.
Because
So,
I go through that your PDF and some videos. So
hmm,
in that thing they are saying that like LSTM. So it will remove the unimportant word and keep it the
hmm,
important word.
hmm.
So how that was decided that it should be keep
Okay. Well,
first
how
one?
to forget and how to remember?
Yes, yes, yes,
There's weights will be there, right? Suppose a WF, forget gate. This will have, let's take point 2, right? Where is forget gate? So let me go back. Yeah, you can see the forget gate, right? Forget gate. So just consider that a particular, it's going to take every word or every character based on how we train, right? So this particular word need to be forget or not. For example, let's consider that a particular word need to be forget, isn't it? Let's take this is machine learning, and ease is not required. It feels that it has to forget. Then it's going to get what? So it's going to get very less weight, so that it's not going to go through the threshold. Whereas when it comes to input gate, again the same case, whether a particular word need to be forward or not. So it's going to get better weight, so that it's going to pass through the threshold. Only when things that pass the threshold will move forward, right? That
so
is how
sir,
it's going to. Yeah.
and then WF that your weight. So who will decide that? That is decided by me only. That random weight,
The
whatever I am giving.
parameter, it's a parameter. So how it is going to be decided? By forward propagation and backward propagation.
Yes.
So it's going initially it's going to let's take point 1, point 1,
Yes.
right? And
Right.
later on, based on the error calculation, based on the error, it's going to recalibrate the coefficients, right?
Yes. Yes.
So the same thing, parameters, and it's going to adjust the weights. Suppose if this is really got, what has you forget, it has to, no, it has been considered that it has been remembered, then obviously it's going to throw error. So the error will increase. So again, it's going to go back and adjust the weights, isn't it?
Yes. Yes.
That is how it's going to work.
And sir, one more term that they are saying about the learning rate. So that
Hmm.
is a constant. That is a constant value. So
No, no, it's not a constant value. In deep learning, even though it starts with, let's take 0.01, it's going to keep changing it. So it may increase or decrease. Let's take point, it may become 0.0001 also.
okay.
And then when it comes to backward propagation, I think I forgot the backward propagation part. The only difference here is like, for regular RNN, it's going to be dou L by, we need to calculate dou L by dou W, but it's not possible directly. So we need to calculate this whole thing. We need to sum this dou L by dou HT, dou HT by dou HT minus 1 multiplied by dou HT by dou HT minus 1 by dou HT minus 2, and so on and so forth. When it comes to LSTM, because we brought this CT minus 1 and all, it will slightly get changed.
It will be some.
So you can see that we need to calculate this one, dou CT by dou C minus 1. When it comes to GRU, GRU for backward I haven't mentioned the same thing, the same formula. It's going to consider even the same formula. There won't be any much change. I think that's the reason I was avoided. But the way we calculate HT minus 1, CT minus 1 will change. This part will change. The way we calculate HT minus 1, CT minus 1, because it has only 2 gates to calculate this, right? Whereas in LSTM, we have 3 gates.
And
that's the difference.
CT minus 1 is the previous times in that.
Right. Because
Yes.
directly not possible, so we need to keep on chaining. The neural network is going to be like a chain, like layers, right? We need to go back and adjust the weights.
And so that hidden layer number of neurons means that how we will decide that means how much
A trial and
that-
error. So we can, trial and error. So again, it depends on how much resource you have. If you have good system, you can go with, here you have given a very limited number of neurons, right?
Yes.
So we can't, there is no formula to calculate the number of neurons that you have to use. So you need to keep on trying it. So you need to look at the accuracy and find out whether it works or not. That's the only way to do that. There is no formula so that you can find out the number of neurons that it has to have in one layer. But even number of layers, we can't decide it. Usually, based on the experience, we can say 3 to 10, but even that can't be a short formula.
So then, sir, it is better to take a large number of neurons. Then after we go, because we know
First
that.
of all, you have to have resources, right? You need to let's take that the production system being given. You don't even have GPU. Then what do you do? So you can't go with large number and then keep on decreasing, right?
Yeah.
So you need to consider even that. And of course, the accuracy is the dictating factor at the end. So how much loss or how much accurate the model is, that is what matters.
Sir, I have a doubt about this Google collab. So there we can need to change it to GPU, right?
Yeah, we can change the GPU, but GPU, the Google Colab is basically provided by Google. So what they did is they added few systems with GPUs. The problem is that when we use Google Colab, let's say they provide a platform wherein we can change to GPU or TPU also. They have even TPUs they're saying that it's much better than GPUs. And of course, CPU. The problem is that let's say this number of GPUs they have given. It is free, right? Even if it's paid version, they have very limited of GPUs. Suppose if you have 100 users, this can handle only 100 users. So just consider that you are the 100th user, right? Another user been added, then you will be exited. The session will get exited. So when you're running it, there is every possibility that it will be discarded anytime. We don't use it in production. Even though you can, Google Lab is free GPUs, but real time it's not going to replicate the real time environment, right? And moreover, it is going to keep on disconnecting. For smaller stuff, obviously you can use your own system.
So for practicing and all, we can use that, right?
Practicing you can use it, but still there are issues like practicing in the sense again it has to replicate the real time environment, right? So if you keep on practicing in Google Lab and once you hit the production, then if it's not matching it with the real time production, then what do? It's better to do it in your own system.
Yes.
There are issues with Google Colab. I personally don't recommend Google Colab, even though it is very attractive because they provide free GPUs and TPUs. Right. Even though it is difficult to handle it in our own machine, it's better to do it in our own machine itself. Because that's how whatever the problem you face it in your machine is going to be exactly the same as it in production. That's the reason. Yeah. Any other questions?
Yes.
Yes.
All right. So don't worry about text data, how to implement it on text data. In fact, it's not just RNN, LSTM, GRU, and thereafter many other architectures came in. I mean to say encoder, decoder, attention, self-attention, and transformers. So mostly we are using transformers. Most of the models that you see here are transformer-based models. We'll see
Yeah,
the
sir.
whole evolution.
This word, because while going through this topic, this encoder, decoder, this words was same. So I
Hmm.
just understand that the computer will not understand English words, so it will be changed to some values.
Okay.
So no, only that portion because I understand.
No, no,
Because
no,
I
no, 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 no. That yeah, I got your point that text data converting from text data to this one, the odd embeddings we call it as, right? That is
right.
different. Encoder decoder by itself is an architecture,
Oh,
neural network architecture.
oh, okay. Yeah, because on that time
Encode,
I saw that some word these types of
yeah, this is going to be like this. An architecture itself. It's not. It has nothing to do. It has nothing to do with the converting strings to numbers. Only
okay.
after we, when we provide input text data, it's we do all the pre-processing stuff and then we feed that data to the architecture.
Oh, this is architecture.
Yeah, this is an architecture. All right. Any other questions? All right. Please go through all. Yeah, go ahead. Someone
No,
says.
no, no. I'm good.
Okay. So please go through the PDFs from interview perspective. You need to remember. Unfortunately, in fact, it's not necessary to remember everything. We need to remember how to implement it. But from interview perspective, as a beginner, there will be an extra burden that you have to remember all this. Okay. So I request you to remember like what has been taught. So the flow, the diagram, and each gate, the formulas, and this formula. You not remember the whole thing. It's in fact the same, right? So here, yeah, we got dou city by dou city minus from LSTM and GRFs. For RNN, we don't have the CT and the CT minus. We have only HT, right? Dou LT by dou HT, dou HT by dou HT minus 1. This whole thing is going to be the product of it. And then finally, is going to have dou HT T by dou W. So that's the only difference that you can see. All right. Any other? Thanks for joining. We'll continue tomorrow. We'll get into generative AI from tomorrow onwards.
Thank you.
Okay, thank you.